The simulations on the previous page reinforce what we have observed about patterns in random sampling. One, proportions from random samples approximate the population proportion P. So sample proportions average out to the population proportion. Kind of like we mentioned, if this is your P, in the last example it was 0.10, all your data values for the sample proportions should go, maybe they'd be a little larger, a little smaller, but they'll probably narrow in somewhere very close to P and make a bell-shaped curve around it. Larger random samples better approximate the population proportion, so large samples have sample proportions closer to P. In other words, a sampling distribution for large samples has less variability. The distribution of sample proportions appears normal, at least for the examples we have investigated. We can describe the sampling distribution with a mathematical model that has these same features. The sampling distribution of sample proportions. For a categorical variable like we've been talking about, whether or not a community college, or whether or not a young adult is enrolled in a community college or not, there's no, the variable is not a number. It's yes, they are enrolled or they're not. Imagine a population with a proportion P of successes. For example, for the variable gender, imagine a population of part-time college students with P equals 0.60 female. Oops, why did I have to get that? Note that a success is the category of interest. It is what we are counting. Here, a success is female. Usually we say the word success as female, and then what's the opposite of success? Fail is male. That's so we're not saying we want, female is better than male. Just the thing we're trying to see is someone a female or male? That's all. Since we've specified female, we say that's a success. But if it was the other way around, we said 0.60 is the proportion of female students. Well, then that means that 0.40 is the proportion of male students. So we could have easily been counting that instead, and we would have said male is success and female is opposite of success. So it's just, don't take offense at it, I guess. We create a mathematical model that describes the sample proportions from all possible random samples of size n from this population. The model has the following center, spread, and shape. Center, the mean of the sample proportions is P, the population proportion. The spread, the standard deviation of the sample proportion is, it shows okay, let me get a different color here. The square root, so you can see it really, hopefully better. Square root of, big kind of calculation here, P times 1 minus P over N. So remember that P is kind of like the probability or the population proportion, and N is your sample size. The standard deviation of the sampling distribution is also called the standard error. The shape. A normal model is a good fit if the expected number of successes and failures is at least 10. We can translate these conditions into formulas. So n multiplied by p is greater than or equal to 10. So when they say at least, they mean greater than or equal to. I'd like it to be at least that, or equal to or greater. And n times 1 minus p is also greater than or equal to 10. Now let's make a comment. The distribution of sample proportions for all samples of the same size is called the sampling distribution of sample proportions. In a simulation, we collect thousands of random samples to examine the distribution of sample proportions. But when we model this distribution, our model describes the sampling distribution that comes from all possible random samples of this size. Let's see, move down here. Now let's look at an example of applying the model for the sampling distribution. Let's apply this model to our previous example about the population of part-time college students to see how it compares to our simulation. Recall that we assume the population of part-time college students is 60% female. We selected samples of 25 part-time college students and calculated the proportion of females in each sample. N equals 25, capital N. The simulation is thousands of random samples, each with 25 individuals. Mathematical model, all possible samples, each with 25 individuals. The mean of sample proportions is 0.6 in the simulation and 0.6 in the mathematical model. The standard deviation of the sample proportion is 0.097 in the simulation and 0.098 in the mathematical model. The shape of the distribution of sample proportions is approximately normal in the simulation, but it's normal because these conditions are met in the mathematical model. Those two that they mentioned, that NP is 25, because N is 25, times P, which is 0.6, and that's 15. And they said, as long as that's greater than or equal to 10, then you're normal. And also the other thing we were supposed to check is that N, which is 25, times 1 minus P, which is 0.6, is that actually greater than or equal to 10? Let's see. N was 25 times 1 minus P, 0.6. That's 25 times 0.4, because 1 minus 0.6 is 0.4. And 25 times 0.4 is 10. And that works because we wanted both of those to be greater than or equal to 10. The top value, 15, was greater than. The bottom value was equal to. So we're good.